Sure.
We also have the talk, that's great. He's going to give us an update on the LOFAR organization team.
Okay, well, thanks. It's a pleasure to be here. I think the last time I was here for also a meeting that Whaley organized, a very intense workshop. That's what I remember, especially if you, of course, are in discussions with Whaley. They're always going to be intense. Right, so that's, I think it was actually even in this room. But today I will talk about the Reionization Key Science project. So that's a large program that we started in 2004 already, before LOFAR even existed. And I'll give you a current status update where we are. But before I go into that, I mean, many of you, they work on scintillometry and maybe other topics. So I will give also a general introduction. So when I talk about reionization, I just not only mean reionization, which is the last part. Let's say if you take the first 1 billion years of the universe, that's the last phase where sort of most of neutral hydrogen became ionized. But in general, I also talk about the cosmic dawn, which is the part that preceded reionization, and then also the dark ages. And I'll explain what these means, what these mean in a moment. Now the interesting thing is that even though this is a 1 billion year sort of era, it's really mostly uncharted. So most of what is happening between, let's say, the cosmic recombination and reionization is largely uncharted. So we actually know more about recombination than we know about reionization, even though what happens in this era, so reionization, but also the cosmic dawn, forms the foundation of the present-day universe. So many of, especially during reionization, many of the sort of building blocks of present-day galaxies and feedback effects and enrichment, etc., and the transitions of population 3 to population 2, etc., stars happened. So it's a very interesting era. So why study this first billion years? So that's sort of summarized in a couple of bullet points here, and obviously there's much more than this. So when I talk about the dark ages, it's mostly this sort of very high redshift regime of about redshift 30 to 200, and there everything is nice and linear. So it's a little bit like the cosmic microwave background, right? The theory, at least in standard physical models, is quite well understood. So you can study the usual things that makes everybody in that studies the cosmic microwave background happy as well, such as the dark matter power spectrum or the mass power spectrum. The good thing of the dark ages is if you study it, for example, via hydrogen, you can also look at the evolution. But if there is something going on with the dark matter, you have annihilation, for example, so if dark matter is not maybe what we think it is, you will also immediately see the imprint during the dark ages, especially on smaller scales. And whereas in the CMB, these smaller scales cannot be measured because of silk damping, in for example, neutral hydrogen, you can measure those small scales as well. So there are things you can do during the dark ages that you can't do during, for example, with the cosmic microwave background. And there are many other things you can study. Then as time progresses, you go to lower redshifts, right? Dark matter grows and under the influence of gravity. So you start forming the first structures. The first stars appear, maybe the first black holes, and they're thought to be population 3 stars with a primordial abundance. Right, so they're not the kind of stars that you see around today. Now, once you get stars, of course, you also get radiation, and this radiation has its impact on, for example, the spin temperature of the gas, and this will be very important for the observables that you have in neutral hydrogen. And also you have heating sources, and these sources, for example, via X-ray heating, X-ray binaries, will heat the gas, and this will also change the spin temperature. And again, this has a very strong observational effect. I'll come back to all of these details in a moment. And then finally, right, of course, stars, the number of stars keeps increasing. Maybe you get mini quasars from the first black holes. So you get more and more radiation, and the gas starts ionizing slowly. You get feedback, you get the first metals, you have that transition from population 3 to population 2 stars. Galaxy formation is really starting to happen. and you get the emergence of the visible universe. Now, with present-day telescopes, we might hope to study this, what is in the box here, let's say with these planned instruments or with present-day instruments, and I will come back to LOFAR, of course, in much greater detail. The dark ages, you really need to go above the Earth's ionosphere, which is a big issue at low frequencies, and you have to go to space or some lunar-based, use some lunar-based instrument. And I will show an example of one of those instruments that we're currently involved in. So there are many reasons why to study this first billion years. Now, what's the evidence for reionization, especially, I say, low redshift reionization? If I would have been here 15 years ago, the first results of WMAP suggested that reionization occurred around redshift 20. Now, if that happened around redshift 20, it's much, much harder to observe than if it's happening around redshift, let's say, below 10. Right? And there's mounting evidence now. So everything that I will show now would not have happened if WMAP initially had been correct, that reionization happened at redshift 20. The evidence is now that it's happening actually relatively recently, let's say just above redshift 6. Now, what's the evidence for this? And probably many of you have seen this many times before. But if you look at what I call now low C, low redshift quasars, talking about redshift 5 or 6 in our eyes is low redshift, right? You start to see a very clear Gunn-Peterson effect, right? So if you look at these spectra of quasars, you start seeing these very large dark gaps here. And these dark gaps mean that the optical depth for absorption of emission from the quasar, UV emission of the quasars, is very large. So the optical depth, as you go from the sort of redshift 5.7, you go up to redshift, let's say, above 6, you start seeing these very empty regions that you don't see at these somewhat lower redshift quasars. That's translated here in an optical depth, which is very rapidly increasing around redshift 6. So this was the first sort of really strong argument that reionization ends roughly around redshift 6, where the optical depth increases very rapidly as you go to higher redshifts, and then rapidly decreases as you go to lower redshift. So there might still be, I mean, don't think of this as being a very large density of neutral hydrogen, because even a small trace of neutral hydrogen of order 10 to the minus 5 can already give you these sort of optical depths here of order unity.
You said that 15 years ago people thought that the reionization was started at redshift 20, so what changed? What was wrong with the...
So I'll come to that in a moment, but basically they overestimated the Thomson scattering optical depth of from the CMB by quite a large amount, and that means that electrons were ionized at high redshifts. So I'll come back to that in a moment. So if you look at Lyman alpha emitters at redshift, let's say 5 or just above 6, you see this sort of luminosity function here. But if you go to 7.3, the predictions were that, this is actually in time not a lot, but the numbers drop quite dramatically. So this has been has been suggested. It's not like that these Lyman alpha emitters disappear. They're still there. They're actually in quite small ionized bubbles. And for this Lyman alpha emission to sort of reach us, by the time this Lyman alpha emission reaches the edge of the bubble, it needs to be redshifted out of resonance. Otherwise, it's simply absorbed at the edge of the bubble. And that only happens when the bubbles are large. So another possibility is that these sort of Lyman alpha emitters are still actually in quite small bubbles. And therefore, also that probably the neutral hydrogen density is still quite large. So that's another indication that there is quite some neutral hydrogen left around redshift 7. The same with this high redshift 7.5 quasar. If you do the models, you look at the spectrum, you see this sudden cutoff here, and this is sort of very noisy. If you do the calculation for the optical depth, or the neutral fraction in this case, you find a 2 sigma lower limit of 0.27. So again, right? A significant fraction of neutral hydrogen at redshift 7. And then coming back to your question, if you look at the latest Planck results, they suggest a low Thomson optical depth for Thomson scattering, suggesting that reionization sort of happens around a redshift of 8. Now, with the first results from WMAP in the first releases, this was not 0.05, but something like, I remember maybe 0.16, which means that the optical depth is much larger, which means you have to have a higher density of electrons to get that, and the only way you get this is to have reionization occur when the universe is smaller, and therefore the electron density was higher. That leads to a higher optical depth. So it's literally a direct translation of this optical depth to a redshift of reionization. So basically they were wrong, WMAP. Right? The later WMAPs, they had lower optical depths, and then Planck came out. They also find a very low optical depth. And much lower than this you can't do, because even a little bit lower than this would actually push this below redshift 6, where we know reionization has happened. So it's really happening at that last sort of redshifts where it can actually happen. Now, so this is evidence that reionization occurred relatively late. So low redshifts, just above redshift 6. Now, if you look at the galaxies, then, right, galaxies have now been found probably up to redshift 11, right, also via lensing. But these brighter galaxies are really the tip of the iceberg. These are not, if you just integrate all the luminosity and emission of these brighter galaxies, they're by far not enough to ionize, reionize the universe. So this is really the tip of the iceberg, but it's not responsible for reionization. So whatever we see out there with telescopes, right, these little light bulbs, right, they're not doing the reionization. There must be much smaller galaxies at much lower luminosities. So it's these mini halos that are causing probably a reionization. Now, of course, right, so this is a summary of the observational evidence for reionization, and just to put it right in a summary, reionization probably roughly happens around redshift 8, right? It started maybe around redshift 10, and then around redshift 6, right? It sort of ended. That's sort of probably the common outcome. Now I put one more extra piece of evidence, right? That's the EDGES result, and I'll come back to that later on. The EDGES result suggesting that neutral hydrogen in absorption has been seen. I just put it as a separate topic here. All right, so everything we see is sort of circumstantial evidence still, maybe except for the Thomson scattering for reionization, all right, with sort of this one-line summary. But the details of this are still largely unknown, and a complementary tracer obviously is the neutral hydrogen or the hydrogen itself. It's really volume filling, it covers all scales, right, and is actually tracing what is being ionized and what forms the stars and what forms the galaxies. All right, so hydrogen itself. Now that is what we, of course, are after with LOFAR, and what many people are after with other instruments as well. Now, if you take a theoretical model that models the brightness or the intensity or the brightness temperature, I'll come back to that in a moment, of neutral hydrogen, you would probably see something like this, right? You see brightness temperature, so this is in millikelvin. Now, just to put this in perspective, the galactic foregrounds at these frequencies or redshifts are several thousand Kelvin, and maybe here several hundred Kelvin, and the fluctuations on top are tens of millikelvin. So it's an extremely faint signal on an extremely bright foreground. Now, of course, as a theorist, you don't care about that, right? You simply simulate this, and this is what you would see happening in such a simulation. Right? You see fluctuations in the brightness temperature due to density fluctuations, spin temperature fluctuations, and then at some point when reionization happens, it sort of ends here, right? All these patches are ionized. You get also fluctuations due to inhomogeneous ionization. All right, so that sort of summarized what I just said in these three things here. All right, so just to put one equation up, right? So this is the well-known equation for the brightness temperature of 21 centimeter emission as function of redshift, for example. And it's set mostly by ionization itself. Of course, if everything is ionized, you have no emission. You have density or baryonic density fluctuations, which cause, of course, intensity fluctuations in the signal. You have your general cosmology in here, which is sort of known. And then a very important one is the difference between the spin temperature of hydrogen and the radiation temperature. At higher redshift, this term really dominates over that term. At lower redshifts, this ionization term starts dominating the fluctuations, because you basically go between maybe 1 and 0, where you have ionized. This is 0. When it's fully neutral, it's 1. So you get above order 30 millikelvin fluctuations. But this number can be very, very large. It can go from 0 to much larger than 1. And therefore, in the cosmic dawn, where this dominates, the temperature fluctuations can be much larger. Now, another thing, and I talked about the spin temperature, what is really happening is, what changes this spin temperature? Now, the spin temperature is in principle set by many things. It's set by the radiation field, like the cosmic microwave background. Early on, spin temperature is equal to the CMB temperature. Therefore, you see nothing. That is pre the dark ages. So from redshift of recombination 1100 down to about 200, the universe is basically you don't see anything in terms of neutral hydrogen. Only at redshift 200 this starts to change. But then when you get the first stars, as I mentioned, they emit Lyman alpha radiation, and Lyman alpha radiation can couple the spin temperature of neutral hydrogen, for example, to the gas temperature. And because the universe is adiabatically expanding, the gas is colder than the CMB temperature, and the moment you start getting radiation, Lyman alpha, you couple the spin temperature to cold gas, but you see it against the CMB, hence you start seeing it in absorption. Now that's called the Waldhausen field effect. So
this is the second time in the history of the universe where the spin temperature is coupled to matter temperature, right? Also, after recombination, it's still coupled to the
CMB. After recombination, you mean?
After recombination, it's still coupled to matter.
No, it's coupled to the CMB temperature.
So
CMB, yes.
On recombination.
Yes.
There's no phase.
No, only in the dark ages it starts coupling to the matter. Then it decouples again. So I will show that now. So so basically up to here, it's basically the CMB temperature equal to the spin temperature. That's why you see nothing. So this is a relative brightness with respect to the CMB. So there's always the 2.7 1 plus E temperature. But if you do it relative to that, then here it starts decoupling, more or less at redshift 200 it starts. This is a very strange scale here, but roughly at redshift 200 it starts decoupling. It couples to the cold gas temperature. That's why you start getting it in absorption. But that coupling becomes inefficient, so you actually go back to the CMB temperature. And then here is where you start getting the first stars, Lyman alpha coupling. Now, underneath you have the gas temperature basically going like this. So that's why you have these dips up to here and then up to here. And then while you get the first stars, you also get the X-ray heating. The X-ray heating makes the gas get warmer again, but the Lyman alpha coupling is still going on. So the Lyman alpha coupling now couples to the warmer gas, and therefore it's going up until you reach a saturation point here, and then of course stars are being formed more and more, and reionization itself kicks in, and then everything disappears. So that explains what we call the global signal, and that's of course what EDGES is trying to measure, It was actually going after this sort of feature here.
Maybe it's too much for this talk, so just tell me, I'm still confused about this Waldhausen effect. That sounds interesting.
Yes, well, we can talk offline about that. Now, of course, this is one picture here that I just showed, But of course, if you change the Lyman alpha emission by increasing it or decreasing it, you change the depth of the feature, the shape of the feature. The same holds for the heating via X-rays. If you change the X-ray heating then of course if you have no heating, you just keep following very cold gas, so this feature gets very deep. But if you heat a lot, then you might not get any feature at all. So by measuring this global feature, you can actually say something about the heating and the Lyman alpha emission and these sort of cosmic dawn effects. Now this is not what we measure, right, with an interferometer. With the interferometer you don't measure the global average, you measure the fluctuations. So if I take this equation that I just showed, and I promised that was the only equation, but that's not true, this is another equation, right, you actually just linearize it, right, right, you get, so you basically linearize that equation in fluctuations, then you get fluctuation due to cosmology, reionization, Lyman alpha sources, X-ray heating, and also peculiar velocities. And then, of course, you can Fourier transform these and then multiply it with itself. Right? You get a power spectrum out, which has a whole bunch of terms that depend on these effects. Now, I will not go into the details of this, but obviously, by measuring the power spectrum, what we ultimately want is to disentangle many of these effects. And this is not necessarily unique, of course. Right? So this is not, right, this does not promise to solve all the problems, right? You still probably want to couple this to those sources that you see and other effects. Now, because we're not measuring a global effect, but now fluctuations, those fluctuations are smaller than that 30 millikelvin or these sort of, right, just going back maybe, right, this can go as deep as minus 250 millikelvin. This is about the deepest you can get. And keep that in mind, because I'll come back to that when I talk about edges. Right, the fluctuations are much smaller. They're of order several millikelvin on, let's say, half a degree scale. And of course, they change as function of scale. That's the power spectrum. But they also change as function, as you can see, of redshift. So, right, you can get very large fluctuations, for example, here during the cosmic dawn. They're much less here during the reionization, but they might be much easier to observe here because the galactic foregrounds are not as bright at lower redshifts. This is a beautiful simulation so Andre Messinger, how he shows how the power spectrum as function of redshift evolves. So this is redshift, very high redshift. You're sort of in the, right, starts off at, now we're in cosmic dawn. You see very rapid changes, very large signals. And now we're going to reionization here. Signal goes up, halfway reionization, and then, of course, when you have full reionization, it disappears. Right, so you see this changing of the power spectrum as function of redshift, and that's ultimately what we want to measure, of course. But because the fluctuations are so small, it requires a very large instrument. So that brings me to interferometric 21 centimeter signal measurements. Right, so many of these experiments are ongoing. You probably heard many of them, paper, right, GMRT, MWA, LOFAR, etc. But they're extremely difficult experiments. Let me say that from the onset. This is not an easy thing to do. The signal is extremely faint, millikelvins on hundreds of kelvins, thousands of kelvins, foregrounds. It's affected by RFI, by the ionosphere. The foregrounds are polarized. You have instrumental distortions, and then the calibration and signal processing itself can cause problems. All right, so these are sort of the four large power spectrum detection experiments, and of course the GMRT was the first, and Whaley was one of the first people, of course, going after this with the GMRT, and also publishing the first power spectrum results. There's MWA in Australia, which is a more compact array, wide field of view. Right, these are dishes, obviously. And then in South Africa, there was paper, which is an ultra-compact array of these sort of receivers here in a very redundant configuration. Now this is now stopped observing and is transforming itself to HERA, and then LOFAR in the Netherlands. Now this is just the same, right, but now all the power spectrum upper limits. Now I don't expect you to see all the details here because it's very hard to see, but all of them have published upper limits now. We're certainly not in a detection regime yet, but they have all published upper limits on the 21 centimeter power spectrum. Now, for example, with GMRT, you see many upper limits. This is the deepest one. As you can see here, you're still quite far away from a signal. Similarly for NWA, which only published a few hours of data, but you're still many orders of magnitude away from a detection. Similarly with LOFAR, we have an upper limit. And then paper also published an upper limit, which was the deepest, but since a week they have retracted that result because they figured out that their way of analyzing things, and I'll come back to that in a moment, removed 99.99% of the signal. So if there was an EOR signal, 99.99% would have been filtered out. This is what they say in their own retraction. Now, this is something that keeps us busy and worried. What do we do to the signal if you have thousands of kelvins and you put a few millikelvin signal on it and you start processing it, calibrating it, removing foregrounds? What do you subtract and what do you add in that process? And I'll come back to that in a moment because we've been very, very busy analyzing this in the last few years. So how do you, well, the beautiful thing of an interferometer is, right, if you measure a power spectrum, you do a Fourier transform, and then you multiply it with its own complex conjugate. Now, the interferometer does already part of that for you, because you're measuring visibilities, which are sort of the Fourier transform of your intensity of the sky. The only thing you need to do is do this in the frequency direction, and the beauty of it is that, right, frequency corresponds to co-moving distance for a emission line. So you can transform frequency, right, and redshift to a distance, so you can actually do this in 3 dimensions. Right, and once you have done that, you have this 3-dimensional spectrum, then of course you can sort of average it in bins and in shells and make either 2-dimensional cylindrically averaged power spectra or spherically averaged power spectra. And I'll show examples of each of these power spectra in a moment. And these power spectra are dominated in terms of their errors by sample variance and by noise. Now, we're currently all more or less in the regime that noise fully dominates. Once we get to HERA, SKA level sensitivities, the sample variance on large scale will start to dominate. But we're not close to that yet. Now, LOFAR. So what is LOFAR? This is really out of date, because Estonia joined and Italy joined recently to LOFAR, but this is from a few years back. So LOFAR is a sort of European collaboration. Most, of course, is led by the Netherlands. We still have sort of 70% of the array, but there are longer baselines extending all over Europe up to a few thousand kilometers. Now, for reionization, what is important is brightness, temperature, sensitivity. So you want to have a large collecting area in a small area. So all of the sensitivity for 21 centimeter comes from that inner few kilometer core. The long baselines we use, for example, to make images and calibrate and see whether we have systematics under control. So this is what a LOFAR station looks like. This is the low band antenna. I'll come and show some results of this as well. But these are the high band antenna measuring between 110 and 240 megahertz. But in general, we measure roughly from 110 up to 170, 175 megahertz. So these are redshifts corresponding to redshift, let's say, 6, 7, up to about 12. Now this can observe at lower frequencies, 30 to 80 megahertz, and can cover up to redshifts of 25 or even further than that. But it's far less sensitive. This is what we call the super TERP. These are 12 of these HBA stations. So most of the sensitivity comes from this area here. So each of these, the 24 tiles, what we call tiles, and each of these tiles has a 4x4 dipole. So 16 dipoles, 24 times 16 times 12, plus a whole bunch of stations out there. And if you look at it from space, you even see it. Right, you see the super TERP, you see these other stations around it. You even see some areas that had been prepared, but then we ran out of money. So they are prepared, but not filled in. That's the reality of things. Okay, so where are we? So we've been observing effectively full-time, almost full-time, since December 2012 in many cycles. We have two primary fields, the North Celestial Pole, right? Nice, it's always there, it's always visible, and 3C196, which is a bright, compact source that we can calibrate on. We've collected by now 2,200 hours on the NCP and about 1,100 hours on 3C186. Today I will just focus on the top here. We have about 5 petabytes of data on disk, and another program that I will shortly mention is a 1,000-hour program with the so-called ArtFark system at the low frequencies to go after some of the predictions from edges. I'll come back to that later on. Now, these are all technical details that you can look at, but effectively we are done observing on this field, and we hope to get still more data on this field in the future, and this will go on for the next 4 years, 4 cycles, so 2 years. Now, we get data at a very high resolution, 3 kilohertz in 2 seconds, about 50 terabytes in about 12 hours of observations. And all of this can be processed, shuffled around in real time on our processing cluster. We flag this data and we then bring it to a lower resolution. This is the data we store. This one is actually not that relevant. This is the data that we analyze, 2 seconds, 60 kilohertz. That's sufficient for the things we want to do. This we simply keep in storage at large data centers for future use, for example, H1 absorption line studies. We make very large images of them that we use to build sky models, but we analyze only low resolution images, as I will show in a moment. Right, and this is of course what we use these for. Now, how do we process all of these data? Now, for about 10 years we had a GPU cluster. We recently upgraded it to a new, what we call Dawn. The previous one was called Dusk. Right, so GPU cluster, 132 GPUs, K40 NVIDIA. This is a picture of it. It has almost a petaflop of processing capacity in GPUs. So this is what we process the data on. We spent also a decade writing all of the software for this, all the way from flagging to imaging. And that's sort of summarized here. So I will not go through the technical details of how we process these data, but there are many, many steps and many loops involved in analyzing these data, from the flagging to standard corrections to data averaging, then directly independent calibration, your standard self-cal with all software that we've written ourselves, then directly dependent calibration, wide field imaging, sky model building, sky subtraction, etc., combining nights, right, improving the sky model, iterating many times here, then at some point subtracting the best sky model, doing wide field imaging cubes, then building residual sky models, then subtracting diffuse foregrounds with also software that we developed, and then ultimately, once we're happy with all of that, we create power spectra and of course ultimately compare them to theoretical models. So all of this software, apart from a few small things, we have developed in-house. Now I will go through the paper that we published last year, and then I will go into things that we are currently doing and what we spent the last few years doing to improve upon what we have done so far. So this is a paper that appeared last year, Patil et al. Again, right, these are the fields. This is the field that I will focus on. Right, that's the other field. Now, again, there are many challenges. Right, the foregrounds are just one of them. They're very bright, they're diffuse, they're polarized, they go through an ionosphere. In the meantime, there's interference. Everything is polarized, including the instrument, and maybe variable. Although at low frequencies, this is less of a problem. Right, the instrument has beams that can vary from station to station. Right, you saw all of these tiles. Well, these tiles you form and do beam forming, but if a tile drops out, your beam is different. So each of these stations has a different beam, and this causes directionally dependent gain errors in your system that we need to solve for. We do that in 122 directions simultaneously. Sensitivity, of course, dynamic range, UV coverage, etc., are all an issue. And then how the heck, I'm on YouTube. How the heck do you actually process all of this data? This was a big nightmare 15 years ago, but then as things progressed, everything became faster and cheaper, right? So we talked about 1 petabyte, but now we have 5 petabytes storage, and it's actually not that expensive. Well, depends. Okay, so NCP Observation. So this is a single run, 13 hours on the NCP, so simple to remember coordinates. The frequency that we do, we observe over about 74 megahertz. We have 48 plus 13 remote stations, 48 core stations, right? 50 terabytes of data. The resolution is about this, but we chop this up in 64 channels. But then in the end, we go to a resolution of about 3 channels, which is about 61 kilohertz. So this is the different averaging here. So this is just an image of the field, right? We make actually something that is as big as the entire wall, just to make a model of the sky, but we only analyze this 3 by 3 degrees. So this sits nicely in the primary beam, so we don't need to worry too much in the analysis about beam effects. This is a much larger image. This is about 20 by 20 degrees, when we've already subtracted off 21,000 sources from the image. All right, so this is an image where 21,000 of the brightest sources have been removed. This is about 10 degrees. Now you can see you reached nicely the confusion limit of several millikelvins. So this is what you have to deal with. Deeper than this, you won't go, except if you start using other foreground removal techniques. And I'll come back to some of them in a moment. Now those 20,000 sources are used for calibration. These are not. These are sources that are left and are not part of your sky model or what you calibrate on. So this is sort of a noise term larger than your thermal noise. Now we have a whole bunch of...
That one was 100 hours, so that you have 2,000. So what's the additional benefit is
it doesn't matter how much you add anymore. This is confusion noise. You never go deeper than this. Yeah, no, this is just an... Yeah, we haven't processed those 2,000 hours. No. We are still analyzing too, because...
Are they a little bit offset from the North Pole?
No. They're all on this field.
So you just hope that you can measure your confusion a bit better? I mean, not be a gain from 20 times more data?
No, we do remove this because this is all spectrally very smooth. Okay. So once you remove that, you hope to hit the thermal noise level, and then you bring it down by more. Yeah.
More accurately.
Yes. No, this is not the final product, obviously. Right, so we then do calibration. Now I will come back to, I'll just skip this because this is very technical. I'll just want to show you that, right, so this is again the same image, but at lower resolution than I showed before. So this is sort of this is slightly higher resolution, and this is the resolution that we actually analyze. So you see the imprint here of the beam. You see a lot of fluctuations here, right? You can see the level of the fluctuations in millikelvin, right? But it's completely confusion noise limited, right? So you see the primary beam here, and this is what we analyze. If you look in Stokes V, which should be noise-like, in fact it is noise-like at any resolution after calibration. Right, so this you need to have noise-like, because the sky in circular polarization at these low frequencies is basically noise, apart from maybe some odd source. So that's a good measure of reliability. Right, and this is all foregrounds. Now, if you make, so this is a spatial slice, but right, of course we have this over all of these frequencies. Right, this is a cube with a depth. Now all of these sources are galactic and extragalactic emission. They're spectrally smooth. So if we make a slice through that cube, not in the spatial dimension, but one spatial and one frequency, that's done here, one spatial, one frequency, you see all of the sources in here, right? Now those need to be removed as well. Now they wiggle around a little bit, and that wiggling is because your PSF is not the same as function of frequency. You need to account for that as well, and we do that. So this has all the sources in it, so once we've removed the sky model after calibration, this is still left. Right, so think of this as a slice, that sort of confusion limited image that I showed before. And this is all the bright sources still in it. This is only the residual sources at the confusion noise in it. Then we build models of this, assuming spectral smoothness. This is the model, and then you subtract that, you get this. But this is a model where we used so-called GMCA, sort of generalized morphological component analysis models. We're currently not doing that anymore, because these models have problems. But what I show is still results using this sort of foreground removal, and if you subtract that from this, you get more or less noise-like looking images. Now then we can look at the power spectra. This is before direction-dependent calibration. So we calibrate in 122 directions for each station. So 63 times 122 directions. Every frequency channel and every 10 minutes we solve for complex gains for all Stokes parameters. Now that's why we needed this big GPU machine. All right, so if we look at the power spectrum before direction-dependent calibration, you'll see a lot of stuff in here, bright foregrounds at these low. This is all foregrounds here, and then you go above here, where you see still a lot of things like ripples and leakage. Much of that disappears after direction-dependent calibration. You still see these stripes here, but that's just a varying UV coverage. That's not something you can remove. That's intrinsic to it's basically signal to noise in your data. Now if you also remove the foregrounds using this GMCA method, you remove, let's say, this part as well, so this model. So then, right, we do the power spectrum based on this here. Right, so this is after direction. So the power spectrum 1, then we had the power spectrum of this one. Now the last one would be the power spectrum of this one. That's what is shown here. Now if you do this on Stokes V, you see that it doesn't match up completely. Right? So that means we haven't reached the thermal noise level. And this has been, we've been bashing our head against the wall for a long time what this could be. And we now understand what this is, and actually we don't see this hardly anymore at the moment. But this is actually a result of the way the data is being processed when we calibrate on longer baselines, but not on the shorter one, but use those long baseline calibrations, right, to calibrate the short baselines. It's a very technical thing, but it's known in signal processing, and it's called leverage. You actually enhance some of the fluctuations that you measure on longer baselines. You then apply them to something that was not part of your data when you calibrate it. Then you increase the fluctuations, and this is exactly what we see here. Now we understand where this comes from, and I'll come to a solution later on. So let me actually then just skip that slide and go, right, so we have now this final power spectrum. The problem is we don't reach the thermal noise level. We don't even reach the Stokes V noise levels. We now understand where it comes from. But we want to be conservative, and in the paper we were extremely conservative, and we took out the Stokes V noise, but not this excess noise. And this excess noise is quite large. So if you now take this point here at K of 0.1, so this is about a degree or half a degree on the sky, then we reached levels of about 300 millikelvin squared. At the lowest, which we published, right, was this here. This is about 80 millikelvin squared. Now remember, the signal is really within brackets of order a few, right? So we're still quite far away from a detection. But just keep this 300 in mind. This is where we were as a reference point at Redshift 9 at K of 0.1. Now let me now come to the signal processing, because this is really the toughest part of the whole analysis, right? And this is what made paper actually retract their result, because they injected a signal into their data processed it, and they removed 99.99% of the signal. Right? And this is because you're injecting an extremely faint thing in something extremely bright, you're calibrating it, and voila, right? Everything that's not part of your model can disappear. So we have spent years thinking about this, and what causes this sort of excess that we see, right? So these are the upper limits here, but they're not considered, right? You don't see these error bars go to 0. Right? That means you have a real upper limit, that you've reached the thermal noise level. We didn't. So this was really the challenge since late 2016, and we've been working on this. So one of the issues was that when we do directionally dependent calibration, so we solve in 120 directions for 63 stations, every 10 minutes, every subband. What happens is if you have diffuse emission like this is polarized, just an example, because in polarized emission most of the emission is diffuse, so it's easy to show. This is what's left after calibration, and that's not good, right? This looks like noise, so we calibrated everything away. Now this is because you have too much freedom in the way you calibrate. You have too many too many free parameters in your model. But if we introduce a cut, right? So we actually don't calibrate on all the baselines, but only on the baselines that are longer than the ones we're interested in. Let's say at 200 lambda in this case. In reality, we do it 250. Right? You see that it more or less comes back. That's because, right, this diffuse emission is now not part of your model, of your data that you calibrate on, so you can't calibrate it away. On the longer baselines, the sky is much more compact. So your sky model is much more complete. So we introduce this cut here, 250 lambda. This says 200, but it's really 250 in the analysis that we do. And that brings back this diffuse emission. Great, problem solved. No, problem is not solved, because what this does is exactly introduce this excess noise that I just talked about, this jump. You see suddenly that on the long baselines, this is more or less what you would expect for the noise level, or for the random errors. But if you do this type of analysis, on the short baselines, it goes up by a factor of 2 to 3. Now this is really caused by the fact that you split your data set in two. And so we've analyzed this in great detail now. We understand where it comes from. So we have a paper coming out on this. And of course, this other people have looked at this. Ewald Weiss, he has looked at this as well, this effect. But how do you solve it? Now the way we currently solve it is if you do this direction-dependent calibration, right, and you look at as function of frequency called channels here, and you have, for example, gains that behave like the truth here, like this blue dashed one. What we do is we enforce some sort of smoothness on the solutions by regularizing it around a smooth solution. In this case, a Bernstein polynomial of third order. It's not, the details are not so important, but you can still deviate from it. That's what you call scenario 2. You see fluctuations around the truth. Now these fluctuations are large enough to take away all this diffuse emission. Even though they're small, they're large enough because the signal is very small. So this is scenario 1. Scenario 2 is when we force the solutions to be spectrally smooth over roughly 3 to 5 megahertz. So that is scenario 2. So you see that there is a smooth line now. It still deviates from the truth, but that's not so important. But it's very, very smooth. So if we do this direction-dependent calibration, we get signal suppression if the gain solution is only regularized and not spectrally smooth. And we get an excess noise if the sky model is incomplete. So we can solve the problem by introducing a cut, but it brings another problem, which is excess noise, in the way we currently do this. Right? This is a problem. So what is the solution is to enforce exact spectral smoothness, right? By going to this scenario 1, for example. But that's a bit computationally much more expensive. But we're working on this now. We have code to do this. All right? So what happens? Oops. So if we have no baseline cut, so the way, right, we analyze it at the moment, right, at the moment we're analyzing it like this. We have a complete or an incomplete sky model, doesn't matter. Let's take the incomplete one that's close to reality. We see that this is the ratio between an input 21 centimeter power spectrum and the output. And you see that it's of order 0.1, this ratio. So we removed 90% of the signal in this analysis. Now this is, right, this is very similar to what is happening in paper. And it doesn't matter whether you have a complete or incomplete sky model, it actually gets slightly better if you have an incomplete sky model. But if you introduce spectral smoothness, it basically pops back to 1. Problem solved. Right? But this is much cheaper computationally than this. But if you introduce a cut and you enforce regularization, then you go back to 1. That's the situation we were in. But the situation we were in had also excess noise, which we actually see here because there's it's a little bit larger than 1. So it's actually introducing extra noise. All right, so what we're currently working on is to basically go to a more spectrally smooth solution, and we have the codes to do this. And maybe have the cut so that we don't suppress and we don't enhance the signal. And this is really what everything is currently all about in these analyses. And I'm running way out of time, I see. So just to show you where we currently are using these sort of methods, within 7 nights, we now reach, using these improved techniques, 45 millikelvin squared. Right? So this is, before we were at 300. So this is much more than you would expect based on 7 nights from, let's say, going from 1 night to 7 nights. And that is because we have far less of this excess noise and because we enforce this sort of spectral smoothness. And based on the data we have, we should be able to reach, this is a nominal signal, we should be able to reach a detection level in about the time that we currently have, which is about 1,500 hours of good data. We have 2,000 or more than 2,000, but 1,500 of it is good. Now, is this interesting what we already have? So I'll show this movie. So this would be the limits. We haven't published them yet because we want to do more tests. But if the X-ray heating is very low, as I said, you go to very deep absorption feature, you go also to very large fluctuations, we would already exceed with very low X-ray heating the current upper limits. So this is becoming actually interesting in terms of placing limits on the X-ray heating in the cosmic dawn. Let me see. Okay, so another result that we recently obtained is that we actually used LBA to go to redshift of 20 to 25. And we do very similar things, except we're using another technique to remove the galactic foreground, and we reach more or less the thermal noise levels there as well. And in terms of a power spectrum, of course, this is not even close to what we do in HBA because the galactic foregrounds are much larger, but we're reaching now levels of order 10 Kelvin. Now you think maybe this is not so interesting, but you have probably all heard the results from EDGES recently, right? That's this experiment here, right, which has claimed a absorption feature, right, of about minus 600 millikelvin. Now, as I told you before, by any normal model cannot go much deeper than about 250 millikelvin. So this is about 2.5 times deeper. Now, this has caused a lot of theoretical papers to appear, one of them being that by Barkana and also Fialkov, where they put some coupling between the baryons in the dark matter, cooling the baryons below that what it can do adiabatically by coupling it a little bit to dark matter, which is much colder. Now then you can get absorption features which are much deeper, but also during the dark ages you can get much deeper signals. But you need a very light dark matter particle, because you need to recoil of the dark matter and give energy. If it's heavier, you just bounce off. And you need, of course, a very small cross-section, otherwise, right, the baryons would just cool and you get all kinds of other effects. So, now the problem with the EDGES result is, and this is a paper by Hills et al., that actually the solution is not physical. You can actually, and it's quite degenerate, you can get many different features with many different foreground models and many different residuals. So it's quite degenerate. And actually a result that came in this morning by work that we're doing with Daan Meerburg, which you all know, of course, and a student of mine and several others, is that if you actually impose physical models both on the foreground and the ionosphere, you add in additional physical model to the 21 centimeter. First of all, you get much stronger residuals, but also you get very degenerate models. So these are the foreground ionospheric models. Now, if you know anything about these things, right, if you get these lines, right, you're extremely degenerate. And actually, if you look at the other parameters, they can be all over the place. But the best model gives residuals which are not the orange one from edges, but the actual result, actually the best solution is unphysical because it has an optical depth of the ionosphere which is much, much larger than it actually is. If you restrict that, the best residuals you get are these sort of wobbly looking features. These could actually be reflections within the system, so you have to be very careful. But if the result is right, then the predictions are also that the intensity fluctuations are going to be much, much larger than predicted before. In fact, they can go all the way up to 1 Kelvin RMS at redshift of about 18. So we started, the result of edges came out 1 week before the LOFAR deadline. So we put in a proposal to cross-correlate all 576 receivers in, well, the LBA receivers here plus a bunch of them out there, and do an all-sky monitoring for 1,000 hours. And we should be able to measure to this level here. So any model that exceeds about this will be a 10 sigma detection after 1,000 hours with ArtFark in this small regime here. So we're measuring only this little band here, which is this peak here. And so, right, so this 14 Kelvin, right, of course, but nominal models which sit somewhere down there, this is nothing. But once you reach a Kelvin, right, maybe after, right, several thousand hours, or after 1,000 hours, you can already exclude all of these models. So that program is running. We're monitoring the entire sky. This is just one snapshot, so this little piece is missing here. Now the final thing I would like to talk about is another interesting thing. So if we go back to this plot, let me go back here, right? So if these models are right, the dark ages signal, which typically was predicted to be minus 50 millikelvin, can go all the way to minus 600 millikelvin as well, right? Because if you have dark matter interacting with baryons, then of course at higher redshift, when the universe is denser, right, the interaction will be even worse, right? So you can get enormous absorption features. Now to measure that, you need to go into space because that is below the ionospheric cutoff. So that brings me to this Netherlands-China low-frequency explorer, which is a piggyback mission on the Chang'e 4 sort of lunar lander mission of China, which is already launched since May. It's already in L2, and we're simply waiting for the lander to be released in a couple of months. And then, right, there is a piggyback mission on there, which is about 10 kilogram unit with 3 tripole monopoles, right, of 5 meters in length. Now, one of the goals is to go after the cosmic dawn and the dark ages. Just to show you a fun movie, this is what these tripoles will look like. Right, these balloons compensate gravity. It's also a little bit festive, but they compensate gravity, right? So this is 5 meters up. It's sort of like a measuring tape that you know these metal measuring tapes, right? You roll them out, they're a little bit buckled so they don't bend. In fact, they told me they could have taken the balloons off and this would have not buckled, but you don't want to take any risks. So this thing is out there now in L2 behind the moon. And it will start taking data in the spring of next year. It's really a proof of principle. It's not extremely, let's say, extremely precisely designed. It was a very quick mission, but it will be the first mission after the early 70s that will measure anything in space at these low frequencies. Now the sensitivity within the 1 to 60 megahertz regime is below that of the sky noise, which is good. Receiver temperature doesn't dominate, which means that the cosmic dawn signal, well, that's a little bit higher here, but that should be measurable, right? That if that was 600 millikelvin, right, within literally 10 to the minus 4 years, you'll be there. But let's say it's not that bad or not that good, right? 10 millikelvin, you reach in a few days. But the dark ages signal, right, is much harder to reach. So there, right, if it's sort of within the mission lifetime, you can reach 10 millikelvin levels. But of course, if it's 600 millikelvin, right, you can reach that much, much quicker, right? You can reach that in let's say, a couple of weeks' time. So this makes, right, this result of edges makes this mission suddenly extremely interesting to exclude these type of extreme models. So that's the last thing. I'm sorry I ran over a little bit, so I'll just leave my general summary that I think the 21 centimeter signal, even though not yet detected, apart from edges, the claim from edges, but I think that requires still confirmation, right, is becoming quite interesting in the last years, right, and is certainly a new and unique probe to, certainly very unique for the dark ages and the cosmic dawn, and also for reionization is extremely interesting to complement the observations that are already there, right. So there are many missions and interferometer experiments going on. There are only upper limits at the moment, although edges claims a detection, but that needs confirmation, I think. And currently, certainly after retraction of paper, LOFAR has the deepest upper limits on the power spectrum, and we are already several factors of 10 deeper now on the data we have, but we have to be very, very careful on the signal processing. And that's really what it's all about at the moment is, are we processing the data properly or not? And for future promises, I think the edges result has really spurred the field again and woke it up after a little bit sort of fell asleep maybe, right? And I know that there's a SARAS-3 experiment. They had already data, but unfortunately they went to Tibet and they had 2 weeks of rain, which never happens there in the site they were. They had 2 weeks of rain, so they couldn't collect any data. So they go back in September and take data, and if this is real, they should measure it in September. And well, I'll leave the rest for you to read, and I'll stop here. Thank you.
Just a philosophical. Obviously, you spend a lot of your time and your energy in this talk discussing the edges to claim.
Mm-hmm.
Now, it seems to be a sociological change over my lifetime that it's become popular that if you have some measurement that you understand, for example, in our days, we saw GMRT, we have residuals. We never went out and claimed that that's exotic dark matter. We could have claimed, oh, this is real, it's exotic dark matter because I don't understand what my residuals are. We just say, okay, the sum of a little thing and what I don't understand cannot be more than what I see, and that's upper bound, that's what you and I do normally. But here's a different group, and it's been done before. If you don't understand the speed of light of neutrinos, you just claim they go past the speed of light. If you don't understand the polarization in your dust, you claim it's gravitational waves. So whenever you don't understand something, now the default position has been to claim it's exotic physics.
Mm-hmm.
That's how we get other people to debug the problems.
But that now becomes the accepted mode, and it's been so successful that by making that claim, you get so many citations, so much attention, you become world famous. That is now the most motivated thing. So you should be going out claiming you've detected, in more exotic product matter rather than published upper bound. That would be. Well,
but I'm sure you don't want to be in the bicep situation, right? You can rise very, very, very far, very high, but you can fall very low as well. So, right? I mean, you take a huge risk.
After the fall, then they would have not having claimed it.
Well, in certain communities, maybe yes, but other people will probably not trust their result the next time.
No, I think they suffered relative to the peak of their stock market. Okay. But the crash after the peak is still so much higher than they had made no claim. That now they're famous. Nobody would have ever heard of that experiment. And these guys got tenure, they got grants, they got funding, they're building new, they got huge amount of money thrown at them to build new experiments.
In that case,
No,
you
yes.
have to extend the existing models in order to explain the data.
Well, let me say, because I'm in some, of course, I'm in some of these funding agency, right? You see these things often happening. The moment there is some, I have to be careful here, I'm on YouTube, but right, that you, right, that there is an opportunity of funding happening, or somebody gets tenure, or blah, blah. You know when these things happen, right? And it happens less in Europe because we're not under those very sort of, there's less pressure, I think, from the funding in that side. But, right, for example, the paper result, I mean, they could have done that 3-4 years ago, right? They could have just injected their signal in there, run it, right? I mean, people blame us all the time, right? Maybe I should rant a little bit here while I'm on YouTube, right? Is, right, you guys don't publish, yeah, because we're very careful. We don't want to fall in these kind of traps, right? We could have published all of these things 5 years ago, 3 years ago, right? We could have, right, we stopped publishing some of this stuff 2-3 years ago because we figure out that we are in fact doing these kind of things, right? And then, right, people publish these things. They go to 22 millikelvin. You tell them, right, this cannot be right. You cannot do this, right? And then, right, 3 years later, they retract it. Now, right, if the edges also has to retract theirs, but of course, right there, you can always say, right, well, the data is right, but right, it's all degenerate, right? It doesn't look good on the field. And you and I were in lensing. And at some point, right, I mean, I started in gravitational lensing and measuring time delays, and we were so happy we measured time delays at some point that it didn't matter which Hubble constant we published, right? It went all the way from 25 to 150, and at some point the community said, right, we don't believe you guys, right? We measured the time delays, right? We just, the Hubble constant that came out, because all models were all over the place, were rubbish. So we destroyed our own field. And we have to be careful, we're not doing it here, right? So we are very careful. Right, we know all the pressures as well. We have them, maybe not as bad as in other fields, but I think this is the psychology of it. Sorry?
Research people were very careful too.
Yes, yes.
They were wrong. They were very careful.
Yeah.
I think they were very careful. Yeah. So the interesting thing is in computing, exactly the opposite is happening. So people make less claims and they start doing what I call computational phenomenology. They just run a code, get a result, and they interpret the result as if that's an observation.
Yeah.
So it's the opposite trend is what you then see in observation, which you point out.
Now, sometimes I'm jealous I'm not a pure theorist because I can just make my data.
Oh, you can be.
I have to deal with 5 petabytes. And of course, it's always the unknowns that kill you, right? I mean, in any simulations we've ever done, forward simulations, we can get to the EOR signal, no problem. But of course, because we didn't put everything in that forward simulation that we run against once we hit something that we don't understand, right? And you say, oh, wait a minute, yeah, of course we should have done this, right? You put that in, yes, we get there, and then boom, you hit something else, right? So this is the step-by-step progress we're making in this field. And sometimes I make the comparison to the CMB, right? It took 25 years to go from a detection of the global signal to the fluctuations, right? But in certain frequency ranges, right, of course, the CMB is above the foregrounds. I mean, we're not even close to that. This is so much more difficult than detecting the CMB, right? So I think people should, right, I mean, of course, in these days, it's very hard to have any patience whatsoever, right? But these things take time. So you want to do it right. Right? You don't want to throw out claims over and over that are wrong because that kills off the field and also the funding, right, for people that do it right. So in some sense, right, I mean, I agree with you that it's, right, people throw out things too easily because what came out in the Hills paper, they could have tested this. They could have just run the models, right? I mean, it's simple. It's not so difficult.
Make a claim. I mean, because it can always be key, you know, everybody else has residuals too. You've got residuals, everybody's got residuals. Yes. You just never claimed that was exotic dark matter.
No, no. I always say, right, imagine that we have this excess noise, but wait a minute, it's actually, right, 1 Kelvin, 21 centimeter, right? We could have done this. Yes. We might be able to exclude exotic models, but we don't claim they are. So that's why there are upper limits. And once we start claiming they're no longer upper limits, right, the burden of proof is very, very high.